In the quiet halls of NASA, beneath the gleam of press conferences and glossy mission posters, there exists a different conversation about Mars. Not the Mars of science fiction covers or inspirational tweets, but Mars as it truly is, unchanging, hostile, and far more mysterious than the headlines dare to admit. Tonight, we will drift beyond the optimism and explore the hidden calculations, the private doubts, the secret measurements that complicate everything we think we know about transforming the red planet into a second Earth. What if the dream of terraforming Mars isn't just difficult? What if it contradicts the very physics of planetary transformation itself? Across millions of miles of darkness, Mars hangs suspended in the cosmic void, neither welcoming nor cruel, simply indifferent. For decades, we have been told that colonizing this world is inevitable, that with enough time, technology, and determination, we will reshape its deserts, thicken its atmosphere, and walk beneath open skies without spacesuits. The vision is beautiful. Press releases speak of timelines and milestones. Engineers sketch habitats with confidence. Billionaires announce launch dates as if Mars were merely another frontier waiting to be claimed. Yet behind this public certainty lies a collection of scientific realities that rarely make the headlines. Problems so fundamental, they challenge the entire premise of Martian transformation. This is not about denying human ambition or dismissing the extraordinary achievements of planetary science. NASA has done miraculous work. The rovers have rewritten textbooks. The orbiters have mapped worlds. But there is a difference between exploration and habitation, between visiting a place and making it home. And in that difference, hidden within technical papers and engineering reports, is a story far more complex than the one we have been told. Tonight, we will examine what makes Mars not just challenging, but perhaps impossibly resistant to the kind of planetary engineering that popular imagination has embraced. The contradictions begin with the atmosphere, or rather, the lack of one. They continue through the soil, laced with chemicals that turn Earth-like dreams into toxic puzzles. They extend to water, radiation, gravity itself, each element presenting not merely an obstacle to overcome, but a fundamental redesign of what human survival might mean on another world. These are not secrets in the traditional sense. The data is published, the measurements are public. Yet somehow, between the raw numbers and the narratives we consume, something essential is lost. The full weight of what Mars actually is remains obscured behind optimism and aspiration. Perhaps the most fascinating aspect is not what we have discovered about Mars, but what those discoveries reveal about our assumptions. We approach the red planet expecting a smaller, colder Earth, a place that might be harsh but ultimately familiar. Instead, we found something stranger, a world that operates by different rules, where the very definition of habitability must be reimagined. The challenges are not simply technical, they are existential questions about human biology, planetary physics, and the ethics of promising futures that may not be possible within any reasonable time frame. As you settle in for this journey through the hidden complexities of Mars, we invite you to share where you are watching from and what time it is in your corner of Earth. Are you drifting off to sleep beneath familiar skies or waking to a new day? Let us know in the comments. This shared moment, scattered across time zones and continents, reminds us that we are all passengers on a planet that already works, that already sustains us without engineering or intervention. And that perspective matters as we consider what it would truly take to create such a place where none exists. Now, let us begin by examining the official story, the version of Mars colonization that fills documentaries and fuels imagination, before we peel back the layers and discover what lies beneath. When NASA speaks of Mars, it speaks in the language of inevitability. Press conferences glow with optimism. Mission briefings are filled with timelines that seem almost within reach. The message is clear, consistent, and carefully constructed. Humanity will walk on Mars, build habitats there, and perhaps one day call it home. This is the official story, the public face of Mars colonization, polished to perfection and broadcast to millions who look skyward with hope. The narrative unfolds in stages, each milestone presented as a stepping stone toward an almost inevitable future. First came the rovers, Spirit, Opportunity, Curiosity, and Perseverance, each more sophisticated than the last, rolling across rust-colored plains, collecting samples, analyzing soil composition, searching for signs of ancient water. These missions were not merely scientific expeditions. They were declarations of intent, visual proof that Mars was not just a distant dream but a tangible destination, one that humanity could touch, explore, and eventually inhabit. NASA's Artemis program, designed to return humans to the Moon, is explicitly framed as preparation for Mars. The official timeline suggests lunar missions in the late 2020s will serve as testing grounds for technologies needed on the red planet. Life support systems, habitat construction, resource extraction, all will be refined in the Moon's lower gravity and harsh environment before being deployed millions of miles farther. The narrative is logical, sequential, and reassuring. We are not rushing toward Mars unprepared. We are building toward it methodically, one carefully planned mission at a time. The timeline NASA presents to Congress and the public typically places human boots on Mars sometime in the 2030s or 2040s. These dates shift occasionally, sliding forward by a few years when budgets are cut or technical challenges emerge. But the overall arc remains unchanged. Mars is coming. It is only a matter of when, not if. Administrator after administrator has stood before cameras and declared that the children watching today will be the astronauts who plant humanity's flag in Martian soil. The message is designed to inspire, to generate public support, and perhaps most importantly, to secure funding. Then there is SpaceX, the private sector's most vocal champion of Mars colonization. Elon Musk does not speak in the cautious, measured tones of government agencies. He speaks in grand visions and aggressive deadlines. His stated goal is not merely to visit Mars, but to establish a self-sustaining city of 1 million people by the end of this century. The Starship spacecraft, still in development, is designed explicitly for this purpose, a fully reusable vehicle capable of carrying up to 100 passengers on interplanetary journeys. SpaceX's timeline is even more ambitious than NASA's. Early unmanned missions were promised for the mid-2020s, with crewed flights potentially following within the decade. These projections have been repeatedly revised, yet the underlying message remains unchanged. Mars settlement is not a distant fantasy, but an imminent reality, one that could begin within our lifetimes. The company's promotional materials show gleaming domes on Martian plains, humans walking without bulky suits under transparent structures, gardens growing in red soil. The imagery is seductive, carefully crafted to transform Mars from a hostile alien world into something that feels almost approachable, almost livable. Other nations have joined the chorus. China has announced plans for Mars sample return missions and has hinted at long-term ambitions for human exploration. The United Arab Emirates has launched probes and spoken of establishing a Martian city by 2117, a timeline so distant it seems more aspirational than operational, yet the message it sends is clear. Mars belongs to humanity's shared future, not to any single nation. The international community, despite political divisions here on Earth, appears unified in at least one vision, that Mars is the next frontier. The public messaging surrounding Mars colonization is remarkably consistent across agencies and borders. It emphasizes resilience, human ingenuity, and the pioneering spirit. Mars is presented as humanity's backup plan, a second home should Earth face catastrophic disaster. It is framed as the ultimate challenge, one that will unite nations and push technological boundaries in ways that benefit life here at home. Water recycling systems developed for Mars could address drought on Earth. Energy technologies refined for off-world habitats could revolutionize sustainability. The argument is compelling. Investing in Mars is investing in humanity's survival. Press releases highlight every success. When Perseverance successfully extracted oxygen from Mars' carbon dioxide atmosphere using the MOXIE experiment, headlines celebrated it as a breakthrough, proof that in-situ resource utilization is possible. When radar detected liquid water beneath Mars's southern ice cap, news outlets framed it as confirmation that Mars could support life, perhaps even future colonies. Each discovery is presented as another piece of the puzzle falling into place, bringing the dream of colonization closer to reality. Yet beneath this carefully constructed narrative, there exists a quieter, more complex story. One that emerges not from press conferences, but from technical papers, internal research documents, and the candid conversations scientists have when cameras are turned off. Government space agencies operate within political realities that shape not just what they say, but how they say it. Funding for space exploration is never guaranteed. It must be fought for annually in congressional hearings where budgets are scrutinized and priorities constantly shift. To secure funding, space agencies must maintain public enthusiasm. They must present visions compelling enough to justify billion-dollar expenditures while avoiding language that might suggest impossibility or excessive risk. This creates a tension between optimism and realism, between inspiring the public and acknowledging the profound technical challenges that remain unsolved. The official story, by necessity, leans toward optimism. It must, or risk losing the political support that keeps missions funded and programs alive. Internal research tells a more nuanced story. Scientists working on Mars missions are acutely aware of problems that rarely make headlines. Engineering reports document challenges with radiation shielding that have no perfect solution. Medical studies reveal physiological effects of low gravity that could prove debilitating over time. Environmental analyses highlight the chemical composition of Martian soil, noting compounds that are toxic to humans and difficult to remediate. These findings are not hidden, they are published in scientific journals and presented at conferences, but they exist in a different realm than the polished narratives shown to the public. There is also the matter of timelines. Privately, many scientists and engineers acknowledge that dates promised for human Mars missions are aspirational at best. Technical hurdles remain that cannot be solved simply by allocating more funding or working faster. Some problems require entirely new technologies that do not yet exist. Others demand testing in conditions we cannot fully replicate on Earth or even on the Moon. The gap between what is publicly promised and what is internally feasible grows wider with each passing year, yet the official messaging rarely reflects this reality. Political pressures shape these narratives in profound ways. When a new administration takes office, space priorities shift. Programs begun under one president are sometimes cancelled by the next, causing years of research and development to be abandoned or redirected. Yet throughout these changes, the Mars narrative endures because it transcends individual administrations. It represents something larger, a vision of human destiny that resonates across political divides. To admit that Mars colonization might be impractical or impossible would be to abandon that vision, and few political leaders are willing to bear that responsibility. The optimism is not entirely cynical. Many of those who speak publicly about Mars genuinely believe in the possibility of colonization. They see challenges as obstacles to overcome rather than insurmountable barriers. This perspective drives innovation and inspires generations of scientists and engineers. Yet it also creates blind spots, areas where enthusiasm overshadows caution, where the desire to achieve a goal leads to underestimating the difficulties involved. The official story of Mars colonization is one of human potential unlimited by earthly constraints. It is a story carefully told, meticulously crafted, and endlessly repeated until it feels like inevitable truth. It shapes how we think about our future, influences how governments allocate resources, and inspires millions to look toward the stars with hope. But like all official stories, it is incomplete. It highlights certain truths while allowing others to remain in shadow, not out of deception, but out of necessity. the need to maintain momentum, secure funding, and keep the dream alive. As we listen to these narratives, it is worth remembering that what is said publicly and what is known privately are not always the same. The gap between them is where the real story lives, in technical reports that acknowledge uncertainties, in scientific papers that document unsolved problems, in the quiet admissions of engineers who know that timelines are more political than practical. The official face of Mars colonization is beautiful, inspiring, and full of promise. But behind that face lies a more complicated reality, one that deserves examination not because it diminishes the dream, but because understanding it fully is the only way that dream might ever be achieved. When we imagine Mars, we often picture a dusty red landscape beneath a butterscotch sky, a place where future colonists will step out in spacesuits and build domes beneath alien sunsets. But there is something missing from this vision, something so fundamental that without it, every other plan becomes exponentially more difficult. That missing element is not water, not soil, not even energy. It is air itself. Mars has an atmosphere, yes, but calling it an atmosphere feels almost generous. To breathe the air on Mars would not be difficult. It would be impossible, not because of its composition alone, but because there is almost nothing there to breathe. The Martian atmosphere possesses a surface pressure of just 0.6% that of Earth's at sea level. Some measurements place it closer to 1%, depending on elevation and season, but the difference is academic. Whether 0.6% or 1%, the result is the same. This is not thin air in the way we understand it on Earth's highest mountains. This is a near vacuum, a wisp of gas clinging to the surface of a dying world. To stand on Mars without a pressurized suit would mean instant exposure to conditions similar to being 100,000 feet above Earth, higher than any aircraft flies, higher than weather balloons venture. Within seconds, the liquids in your body would begin to boil at body temperature, a phenomenon called ebulism. Consciousness would fade in 15 seconds. Death would follow shortly after. But the catastrophe of Mars' thin atmosphere extends far beyond the immediate danger to human bodies. It reshapes every assumption about terraforming, about building habitable structures, about creating a self-sustaining civilization. An atmosphere is not merely something to breathe. It is a shield, a blanket, a reservoir of chemical potential, and a medium through which heat and energy flow. Without sufficient atmospheric pressure, liquid water cannot exist on the surface. It either freezes solid or sublimates directly into vapor, skipping the liquid phase entirely. This means that even if we melted Mars's polar ice caps, even if we discovered vast underground aquifers, the water would not pool into lakes or rivers. It would evaporate into the thin air and drift away into space. This is not speculation. This is physics, as immutable as gravity itself. The question then becomes not just how thin Mars's atmosphere is, but why it is thin, and whether anything can be done to change it. The answer lies not in engineering alone, but in planetary history, in events that unfolded billions of years ago when Mars was still young and potentially habitable. Mars once had a thicker atmosphere, evidence from ancient riverbeds, mineral deposits that form only in liquid water, and isotopic measurements all point toward a Mars that was once warmer, wetter, perhaps even blue. But something changed. Something was lost. That something was Mars' magnetic field. Earth is protected by an invisible shield, a magnetosphere generated by the churning of molten iron in our planet's outer core. This magnetic field extends tens of thousands of miles into space, deflecting the solar wind. A continuous stream of charged particles that pours outward from the sun at speeds of 400 miles per second. Without this protection, Earth's atmosphere would be slowly stripped away, molecule by molecule, carried off into the void. Mars once had such a field. Scientists believe that early in its history, Mars possessed a molten core and an active magnetic dynamo, just like Earth. But Mars is smaller. It cooled faster. Within its first billion years, the core solidified, the magnetic field collapsed. and Mars was left defenseless against the relentless bombardment of solar radiation. What followed was not a sudden catastrophe, but a slow erosion spanning eons. The solar wind began to strip away the Martian atmosphere, particle by particle, year after year, millennium after millennium. Oxygen, carbon dioxide, nitrogen, all the gases that might have made Mars a living world, were carried away into interplanetary space. Measurements from NASA's MAVEN spacecraft, which has orbited Mars since 2014, have revealed that Mars continues to lose atmosphere even today. Approximately 100 grams of atmospheric gas escapes into space every second. Over a year, that amounts to more than 3,000 tons. Over billions of years, the loss is almost incomprehensible. This discovery fundamentally altered the calculations for terraforming Mars. If we were to somehow thicken the Martian atmosphere, perhaps by releasing greenhouse gases from the polar caps, by importing comets rich in volatiles, or by deploying massive industrial atmospheric processes, the question remains, how long would that atmosphere last? Without a magnetic field to protect it, would we not simply be pouring gas into a leaking vessel? Would the solar wind not strip away our carefully constructed atmosphere just as it stripped away the original one? Some estimates suggest that even with aggressive terraforming, a thickened Martian atmosphere might only last thousands of years before significant loss occurs. In geological terms, that is the blink of an eye. The problem is not merely one of atmospheric pressure, but of atmospheric retention, and retention requires protection. There have been proposals, some bordering on science fiction, others rooted in genuine physics, to address this dilemma. One idea involves constructing an artificial magnetic shield at the L1 Lagrange point between Mars and the Sun, a position where gravitational forces balance and an object can remain relatively stationary. A sufficiently powerful magnetic field generator placed there could, in theory, deflect the solar wind around Mars, allowing the planet's atmosphere to gradually thicken over centuries as trapped gases are released from the polar caps and subsurface reservoirs. NASA has explored this concept in preliminary studies. The energy requirements would be immense, the engineering unprecedented, but it is not impossible. Not in the way faster than light travel is impossible. It is merely extraordinarily difficult. Yet even if such a shield were constructed, even if Mars were granted a second chance at atmospheric stability, there remains the question of time. How long would it take for Mars to naturally regain a breathable atmosphere? Estimates range from thousands to tens of thousands of years, depending on the rate of outgassing from the planet's interior and the efficiency of any artificial processes we might deploy. This is not a timeline measured in decades or even centuries. It is a timeline measured in epochs, in spans of time longer than all of recorded human history. There are, of course, alternative theories. Some scientists propose that Mars's atmospheric loss may not be a linear, continuous process, but one that varies depending on solar activity. During periods of intense solar storms, atmospheric stripping accelerates. During quieter periods, it slows. If this is true, then perhaps there are windows of opportunity, times when the solar wind is calmer and atmospheric retention is more feasible. Others suggest that Mars may have experienced cycles of atmospheric thickening and thinning throughout its history, driven by volcanic activity releasing gases from the interior, only to be stripped away again over time. If Mars's interior is not entirely dead, if there remains residual heat and geological activity, then perhaps outgassing continues even now, albeit at a rate too slow to counteract solar wind losses. Recent discoveries have added layers of complexity to this already intricate puzzle. Measurements of isotopic ratios in the Martian atmosphere reveal that lighter isotopes have been preferentially lost, exactly what we would expect if atmospheric stripping has been occurring for billions of years. Heavier isotopes remain behind, creating a chemical fingerprint of loss. Additionally, observations of atmospheric plumes and seasonal variations suggest that Mars' atmosphere is more dynamic than once thought. It thickens slightly during winter as carbon dioxide freezes out at the poles, then thins again in summer as the ice sublimates. These are not trivial changes. They represent fluctuations of up to 25% in atmospheric mass a seasonal breathing of the planet itself. But these natural cycles do not change the fundamental challenge. Mars' atmosphere is not merely thin, it is unsustainable without intervention. Any serious discussion of Mars colonization must confront this reality. We cannot simply build habitats and assume the atmosphere will cooperate. We must either accept that humans on Mars will live forever in pressurized environments, utterly dependent on technology for every breath, or we must commit to planetary-scale engineering projects that may take millennia to complete and require technologies we have not yet invented. This is not to say that Mars is beyond our reach, only that the reach required is far longer than popular narratives suggest. The atmosphere problem is not a minor inconvenience to be solved with a few decades of effort. It is a fundamental barrier rooted in planetary physics, in the absence of a magnetic field, in billions of years of atmospheric loss. To terraform Mars is to rebuild not just its surface, but its very ability to hold on to an atmosphere. It is to reverse the consequences of planetary death. And yet, even knowing this, the dream persists. Perhaps that is the nature of human ambition. We look at Mars, thin air and all, and we see not what it is, but what it might become. We see a world waiting, silent and patient, for the day when we learn to give it back the breath it lost so long ago. As we turn our attention from the atmosphere above Mars to the ground beneath, we encounter something unexpected. The Martian soil, that rusty red dust that has captured human imagination for centuries, harbors a secret that fundamentally changes the equation of survival. It is not merely barren, it is toxic. And this toxicity was discovered not through distant speculation, but through direct measurement by robotic explorers that tasted the soil itself. In 2008, NASA's Phoenix lander touched down in the northern polar regions of Mars and began analyzing samples of Martian regolith. What it found was perchlorate, a chemical compound containing chlorine and oxygen, scattered throughout the soil at concentrations far higher than scientists had anticipated. Subsequent missions confirmed this discovery was not isolated. The Curiosity rover, exploring the equatorial regions thousands of miles away, found perchlorates there too. Then Spirit, then Opportunity. Every landing site, regardless of location, revealed the same truth. Perchlorates are not a local anomaly. They are woven into the fabric of Mars itself, distributed across the entire planet, at concentrations averaging between 0.5% to 1% by weight. In some locations, the levels climb even higher. To understand why this matters, we must first understand what perchlorates do. On Earth, these compounds are rare, typically found only in desert regions like Chile's Atacama, or synthesized for industrial use in rocket fuel and fireworks. They are powerful oxidizers, meaning they aggressively interact with other chemicals, breaking them down. In the human body, perchlorates interfere with the thyroid gland's ability to absorb iodine, a mineral essential for producing hormones that regulate metabolism, growth, and brain development. For adults, chronic perchlorate exposure can lead to thyroid disorders, fatigue, and metabolic dysfunction. For children and developing fetuses, the effects are far more severe. Perchlorate exposure during critical developmental periods can result in permanent cognitive impairment, reduced IQ, and developmental delays that no amount of later intervention can fully reverse. This is not theoretical. We know this from terrestrial studies where groundwater contamination by perchlorates has been linked to measurable health impacts. On Mars, colonists would not be dealing with trace contamination in water supplies. They would be surrounded by it. It would coat their equipment, infiltrate their habitats through airlocks, and permeate every system designed to sustain life. The dust storms that regularly sweep across Mars would ensure that perchlorate particles become airborne, settling on surfaces, floating in recycled air, and finding their way into lungs and living spaces despite the most rigorous decontamination protocols. But perhaps the most profound challenge posed by perchlorates concerns food. Every vision of Martian colonization includes greenhouses, hydroponic gardens, or underground farms where crops grow in Martian soil enriched with nutrients and water. Yet Martian soil is not merely deficient in nutrients, it is actively hostile to life. Perchlorates destroy organic compounds, the carbon-based molecules that form the foundation of all known biology. Plants attempting to grow in perchlorate-rich soil would absorb these compounds through their roots, accumulating them in their tissues. Studies have shown that vegetables grown in perchlorate-contaminated soil on Earth can concentrate these toxins to levels far exceeding safe consumption thresholds. Eating such crops would be like consuming small doses of poison with every meal, a slow accumulation that would silently damage the thyroid, disrupt hormones, and compromise the health of every person dependent on that food supply. The instinctive solution seems obvious: clean the soil, wash away the perchlorates, heat them to break them down, or chemically neutralize them. But this is where the scale of the problem becomes overwhelming. Perchlorates are water-soluble, which means they can be washed away, but only if you have vast quantities of water, a resource Mars offers in limited and difficult-to-access forms. To flush perchlorates from soil intended for agriculture would require processing every kilogram through multiple rinse cycles, consuming precious water that colonists would desperately need for drinking, hygiene, and industrial processes. And where would the contaminated runoff go? It cannot simply be dumped, as it would seep back into ice deposits or underground aquifers that future missions might depend upon. Every litre of water used to clean soil is a litre not available for human consumption. Heating soil to decompose perchlorates presents its own challenges. While temperatures above 400 degrees Celsius can break down these compounds, heating tons of Martian regolith to such temperatures would require enormous amounts of energy. Solar power on Mars is already limited by dust and distance from the Sun. Nuclear reactors could provide the necessary energy, but they introduce complexity, risk, and the need for fuel that must be transported from Earth or synthesized locally. The energy cost of soil remediation at the scale necessary to support even a small colony could rival the energy needs of all other life support systems combined. Chemical treatment methods exist, but they too demand resources. Using bacteria or chemical agents to neutralize perchlorates requires importing biological cultures or chemical feedstocks from Earth, establishing controlled environments where these processes can occur, and managing the waste products they generate. Each solution creates new problems, new dependencies, new vulnerabilities in a chain of survival that must not break even once. The perchlorate problem extends beyond agriculture into the realm of water itself. One of the few advantages Mars appears to offer is water ice, locked beneath the surface in vast reserves. Future colonies are envisioned extracting this ice, melting it, and purifying it for use. But Martian ice is not pristine. It too contains perchlorates, dissolved into the frozen matrix. Melting ice releases these compounds into the liquid water, requiring filtration systems robust enough to remove them to safe levels. Reverse osmosis and ion exchange systems can accomplish this, but they require maintenance, consume energy, and produce concentrated waste that must be safely stored or disposed of. The more water you process, the more contaminated waste you accumulate, and on a planet where nothing can simply be thrown away, every waste stream becomes a logistical burden. There is a deeper, more philosophical dimension to the perchlorate problem. It forces us to confront the reality that Mars is not a blank canvas waiting for human presence. It is a world with its own chemistry, its own equilibrium, its own way of being that is fundamentally incompatible with Earth-based life. The perchlorates in Martian soil are not pollution or contamination. They are an intrinsic part of what Mars is. To terraform Mars, to make it livable for humans, would require not just adding what is missing, atmosphere, warmth, water, but also removing or neutralizing what is present. It would mean chemically re-engineering an entire planetary surface, a task of staggering complexity that goes far beyond planting flags and inflatable habitats. Some scientists propose accepting the perchlorates and adapting to them, rather than trying to eliminate them. Bioengineering crops that are resistant to perchlorate uptake, developing supplements to counteract thyroid disruption, or creating entirely closed-loop hydroponic systems that never touch Martian soil. These approaches have merit, but they shift the challenge from environmental engineering to biological engineering, requiring advances in genetics and medicine that remain speculative, and they introduce new uncertainties. What are the long-term effects of living in a perchlorate-saturated environment, even with countermeasures in place? How do we ensure that protective measures remain effective across generations, especially for children born on Mars, whose developing bodies may respond differently than adults? The perchlorate issue is rarely discussed in popular depictions of Mars colonization. Press releases and promotional videos show astronauts scooping Martian soil into planters, watching tomatoes grow under artificial lights, drinking water melted from Martian ice. These images are compelling, hopeful, and misleading. They gloss over the invisible chemical battle that would define every moment of life on Mars, a constant struggle against a planet that, at the molecular level, is quietly hostile to our biochemistry. This is not to say the problem is insurmountable. Human ingenuity has overcome extraordinary challenges before, but acknowledging the problem honestly is the first step towards solving it. The perchlorates in Martian soil do not make colonization impossible, but they do make it significantly more difficult, more expensive, and more time-consuming than public timelines suggest. They add years, perhaps decades, to the development of truly self-sustaining colonies, because every system must account for this hidden toxin woven into the fabric of the planet itself. As we consider the dream of humans walking across Martian plains, tending gardens under domed skies, we must also imagine the invisible work happening behind those scenes, the constant filtration, the energy-intensive remediation, the medical monitoring, the careful management of every resource in an environment where a single oversight could poison a generation. Mars does not welcome us with open arms. It presents us with puzzles, each one requiring solutions that stretch the boundaries of what we know and what we can build. The perchlorate problem is one such puzzle, and it waits patiently in the red dust for anyone bold enough to come and solve it. The headlines arrive with clockwork regularity, each more triumphant than the last. Water found on Mars. Ancient rivers discovered. Mars had oceans. These announcements echo across news feeds and social media, painting a portrait of a world where water flows just beneath the surface, waiting to quench the thirst of future colonists. The images are captivating. Dried riverbeds snaking across rust-colored plains, polar ice caps glinting in the thin Martian sunlight, underground lakes detected by orbital radar. Each discovery fuels the narrative that Mars is a world of hidden abundance, a planet where humanity's second home is not just possible, but inevitable. Yet between the excitement of discovery and the reality of utilization lies a vast, often unspoken chasm. The water on Mars exists, yes, this is not in question, but the practical truth of accessing that water, purifying it, and sustaining a colony with it, reveals challenges so profound that they fundamentally alter the colonization timeline. What the headlines celebrate and what engineers must actually work with are two different stories entirely. To understand the water mystery of Mars is to first understand where this water actually resides. The most visible water on Mars exists at the poles, locked in massive ice caps composed of both water ice and frozen carbon dioxide. These caps are impressive, stretching across thousands of square miles, gleaming white against the red planet's surface. Scientists estimate that if the northern polar cap alone were to melt, it could cover the entire planet in water several feet deep. This sounds promising until we confront the reality. These ice caps are located at the most extreme latitudes of Mars, regions where temperatures plunge to -200 degrees Fahrenheit during winter. Establishing a mining operation in these conditions would be like building a water extraction facility in Antarctica, except without breathable air, without atmospheric pressure, and with radiation levels that would be lethal within days. The second repository of Martian water lies underground. Orbital radar has detected what appear to be substantial ice deposits beneath the surface, particularly in the mid-latitudes. Some of these deposits exist only a few feet below the regolith, while others are buried under hundreds of feet of rock and dust. Recent findings from NASA's Mars Reconnaissance Orbiter have revealed ice cliffs exposed in crater walls, offering tantalizing glimpses of subsurface reservoirs. But here too, the engineering challenges multiply. Extracting underground ice requires drilling through Martian soil that is harder than concrete in many regions, using equipment that must function in near-vacuum conditions at temperatures where most machinery becomes brittle and prone to failure. Every kilogram of water extracted would require enormous energy expenditure, and energy on Mars is itself a precious, limited resource. Then there is the question of liquid water, the holy grail of Mars exploration. In 2018, scientists announced the detection of what appeared to be a liquid water lake beneath the southern polar ice cap, buried more than a mile below the surface. The discovery generated intense excitement, for liquid water suggests not just H2O molecules, but the possibility of biological activity, of chemistry that mirrors Earth's own. Yet further analysis revealed troubling complications. For water to remain liquid at Martian temperatures and pressures, it would need to be extraordinarily salty, saturated with perchlorates and other dissolved minerals, to such extreme concentrations that it would be more brine than water. This is not the fresh spring we imagine when we think of Martian colonies filling their canteens. This is a toxic, corrosive fluid that would require intensive processing before a single drop could be safely used. The energy cost of water extraction on Mars cannot be overstated. Consider the process. First, the ice must be located with precision, requiring ground-penetrating radar and extensive surveying. Then it must be excavated, either through drilling or surface mining, both energy-intensive operations. The ice must then be heated to convert it to liquid, a process that consumes enormous amounts of power in an environment where solar panels generate only 40% of the energy they would on Earth, due to the greater distance from the sun and the frequent dust storms that block sunlight for weeks at a time. Once melted, the water must be filtered and purified, removing not just particulates, but the perchlorates that permeate Martian soil and ice. These perchlorates present their own labyrinth of challenges. Unlike simple salt, which can be removed through basic filtration, perchlorates are highly reactive chemicals that interfere with human thyroid function and can be toxic even in small concentrations. They exist throughout the Martian environment, mixed into the soil, dissolved in the ice, carried by dust storms. Removing perchlorates requires sophisticated chemical or biological treatment systems, technologies that must be transported from Earth, maintained in the hostile Martian environment, and powered continuously. Each liter of drinkable water becomes not a simple extraction, but an industrial process. Recent rover findings have further complicated the abundance narrative. NASA's Curiosity and Perseverance rovers, designed in part to search for water-related minerals and biosignatures, have discovered that many of the ancient lakebeds and river channels on Mars contain minerals that form only in extremely salty, acidic conditions. These findings suggest that even when Mars had liquid water flowing on its surface billions of years ago, that water was often harsh and chemically hostile. The planet's water history is not one of pristine mountain streams, but of briny, mineral-saturated flows that challenge our assumptions about habitability. Perhaps most troubling is the question of total accessible volume. While Mars contains substantial water when measured in absolute terms, the amount that could be practically accessed and processed for a sustained colony remains deeply uncertain. Some estimates suggest that supporting even a small colony of a few hundred people would require processing hundreds of thousands of gallons of water annually, not just for drinking, but for agriculture, oxygen production, hygiene, and industrial processes. Where exactly this water would come from, and whether the extraction rate could keep pace with consumption, remains an open question that optimistic projections often gloss over. There is also the matter of water rights and resource allocation, questions that seem premature until we remember that every Mars mission will be constrained by mass, energy, and logistics. If multiple missions or nations establish outposts on Mars, who has access to the ice deposits? How do we prevent over-extraction in a region where water cannot be replenished by a planetary water cycle the way it is on Earth? Mars has no rain, no rivers flowing from distant mountains. The water that exists there is finite, a fossil resource left over from the planet's wetter past. The water mystery of Mars is not that water doesn't exist. It is that the water which exists is trapped, frozen, contaminated, and distributed across a planet where everything required to access it, from energy to equipment to human labor, must first be transported across 140 million miles of space. The headlines that announce water discoveries are not false. They are incomplete. They capture a moment of scientific triumph without conveying the decades of engineering development that would be required to transform that discovery into a functioning water supply system. As we contemplate the future of Mars colonization, water remains both a promise and a puzzle. It is the substance that makes life possible. Yet on Mars, it exists in forms that resist easy use. Between the ice caps and the underground reserves, between the exciting radar detections and the reality of purification systems, lies the gap between what we hope Mars can provide and what it actually offers. This gap does not make Mars colonization impossible, but it does make it vastly more complex, more expensive, and more distant than the headlines suggest. Every glass of water on Mars will be a triumph of human ingenuity, extracted from ice, purified through chemistry, and delivered at a cost that earthbound minds can barely fathom. Beyond the surface challenges of atmosphere and soil lies a threat that is invisible, relentless, and fundamentally transforms what human life on Mars could ever truly be. Radiation. The word itself carries weight, conjuring images of danger unseen and damage irreversible. On Earth, we live beneath a protective shield so effective that most people never consider it. Our magnetic field, our thick atmosphere, layers of atmospheric chemistry that deflect and absorb the constant bombardment of cosmic rays and solar particles. Mars has none of this. Standing on the Martian surface is to stand exposed to the naked fury of space itself. The numbers are stark and unforgiving. Mars receives between 40 and 50 times more radiation than Earth. This is not a marginal increase that clever engineering might compensate for with slightly thicker walls or improved materials. This is a fundamental shift in what it means to exist as a biological organism in that environment. Every hour spent on the Martian surface accumulates radiation dose at levels that would trigger evacuation protocols on Earth. Every day compounds the risk. Every year increases the probability of cellular damage, cancer, cognitive decline, and genetic mutation. The radiation does not pause. It does not sleep. It flows continuously from deep space, from distant supernova, from the sun's violent outbursts, arriving unfiltered at the rust-colored plains where future colonists dream of building cities. NASA's public communications about Mars often feature images of surface habitats, domed structures with windows looking out across Martian vistas, astronauts in suits walking beneath alien skies. These images are compelling. They are also misleading if they do not acknowledge the radiation reality that would make such surface living untenable for any extended period. The truth is quieter, darker, more confining than the vision typically presented. If humans are to live on Mars for years or decades, they must live underground. Not as a lifestyle choice, but as a biological necessity. Underground habitats offer the only viable long-term protection from radiation without requiring transportation of massive shielding materials from Earth. Several meters of Martian rock or regolith can reduce radiation exposure to levels approaching Earth normal. Natural lava tubes, if they exist in suitable locations, could provide ready-made caverns requiring only sealing and pressurization. Excavated tunnels could house entire communities, protected by the very planet they seek to colonize. This is not speculation or pessimism. It is physics. The universe does not negotiate, and the radiation flux at Mars' surface is a constant that no amount of optimism can alter. But consider what this means for the human experience of Mars. The glossy renderings of Martian cities with glass towers and surface gardens dissolve into a different reality. Corridors carved into rock, artificial lighting replacing natural day, windows not to the outside world, but to monitor screens showing what lies above. the psychological dimension of permanent underground existence is profound and largely unexplored in public discourse about Mars colonization. Humans evolved beneath open skies, with natural light cycles, visual horizons, and the sensory richness of surface environments. Even Earth's submarine crews, Antarctic researchers, and underground workers experience documented psychological strain from extended periods in confined artificial environments, and they know they will eventually return to the surface, to sunlight, to open spaces. Mars colonists would face something different entirely. Not a temporary assignment, but a permanent condition. Not a sacrifice with an endpoint, but a fundamental redefinition of human environmental experience. Children born on Mars might never stand beneath an open sky without protective layers between themselves and the cosmos. The sensory deprivation, the monotony of artificial environments, the psychological weight of knowing that the surface world above is hostile and inaccessible. These factors introduce variables into Mars colonization that transcend engineering and enter the realm of human neurology, psychology, and perhaps something deeper, the question of what environments human consciousness requires not just to survive, but to thrive. The biological effects of chronic radiation exposure extend beyond individual health into questions of generational viability. DNA damage accumulates not just within a single human lifetime, but potentially across generations. While Earth's natural radiation causes some background mutation rate, the elevated levels on Mars could accelerate genetic damage in ways we are only beginning to understand. Reproductive cells are particularly vulnerable to radiation damage. Some research suggests that multi-generational exposure to elevated radiation could affect fertility, increase miscarriage rates, and elevate the risk of birth defects. A Mars colony is not viable if the first generation can arrive, but subsequent generations cannot be born healthy or cannot reproduce effectively. The uncertainty here is significant and troubling. We have limited data on how human reproduction functions in environments with Mars-level radiation over multiple generations. Animal studies provide some guidance, but the leap from laboratory mice to human populations is substantial. If the radiation environment proves more damaging to human reproduction than current models predict, it would not become apparent until after significant investment and human presence on Mars. This is not a problem that can be solved with a software update or a mission redesign. It is a fundamental question about whether Mars can support permanent human population without extensive genetic intervention or continuous genetic screening, technologies that introduce their own ethical and practical complications. Even with underground habitats solving the surface radiation problem, material science faces formidable challenges in creating adequate shielding for all the structures humans would need. Power generation facilities, mining operations, agricultural spaces, if any attempt is made at surface farming, each requires either massive shielding or acceptance of high radiation exposure for workers. Water can serve as effective radiation shielding, and some designs propose water-filled walls for habitats. But water on Mars is precious, difficult to extract, and using it for shielding means it cannot be used for drinking, agriculture, or fuel production. Every design choice involves trade-offs that cascade through the entire colony architecture. Perhaps most critically, the transit radiation problem fundamentally constrains when and how missions to Mars can even occur. The journey to Mars takes 6 to 9 months, depending on the trajectory and the relative positions of Earth and Mars. During this transit, astronauts are exposed to deep space radiation with minimal shielding. Spacecraft mass is limited, and every kilogram of shielding material is a kilogram that cannot be food, water, fuel, or equipment. Current spacecraft designs offer minimal radiation protection, and astronauts on a Mars mission could receive radiation doses approaching or exceeding career limits established for space travel. Solar events compound this problem unpredictably. The Sun periodically releases massive bursts of radiation called solar particle events or coronal mass ejections. If one of these events occurs during transit to Mars, astronauts could receive lethal radiation doses within hours, unless the spacecraft includes a heavily shielded "zero," adding more mass to an already constrained mission architecture. Mission planners attempt to schedule launches during periods of predicted lower solar activity, but the Sun's behavior cannot be perfectly predicted, and Mars launch windows occur only every 26 months due to planetary orbital mechanics. If solar conditions are unfavorable during a launch window, missions may need to wait years for the next opportunity. This fundamentally changes the vision of Mars cities from something resembling Earth cities transplanted to another world into something far more constrained and alien. Mars colonies, if they exist at all, will likely be small populations living in carefully shielded underground environments, with surface activity limited to essential operations conducted in heavily shielded suits or vehicles for limited durations, with cumulative exposure carefully monitored. The romantic vision of walking freely across Martian landscapes, of cities with windows gazing out at Olympus Mons, of children playing in parks beneath Martian sunsets, all of this dissolves in the harsh light of radiation physics. NASA and other space agencies are not unaware of these challenges. Research continues into radiation shielding, pharmacological countermeasures that might reduce cellular damage, and faster propulsion systems that would shorten transit time and therefore radiation exposure. Some proposals involve generating artificial magnetic fields around spacecraft or habitats, mimicking Earth's protective magnetosphere on a smaller scale. These technologies remain largely theoretical, energy-intensive, and unproven at the scales required for Mars missions. The radiation reality does not make Mars colonization impossible, but it does make it profoundly different from what popular imagination and public-facing space agency communications often suggest. It transforms Mars from a second Earth into a fundamentally hostile environment where human presence requires constant technological mediation, permanent environmental separation, and acceptance of biological risks that accumulate invisibly across time. The invisible killer, as radiation has been called, does not announce itself with immediate symptoms. It works silently, damaging cellular machinery, corrupting genetic information, increasing cancer risk year by year. On Mars, this invisible threat would become the defining constraint around which all human activity must be structured. As we consider the future of Mars colonization, the radiation problem stands as perhaps the most honest indicator of what such an endeavor truly entails. Not adventure in the spirit of terrestrial exploration, but survival in an environment fundamentally incompatible with human biology, without technological intervention so extensive, it raises the question, at what point does human presence on Mars cease to be colonization and become instead a kind of permanent quarantine? We tend to imagine gravity as a background setting, a constant that never changes. On Earth, it is invisible, unquestioned, a quiet agreement between our bodies and the planet beneath our feet. On Mars, that agreement is broken. Mars pulls with only 38% of Earth's gravity. Every movement would feel lighter, every step a small, effortless leap. For the first few days, it might feel exhilarating, like living in a slow-motion dream. But over months, years, and lifetimes, this difference in pull is not simply a curiosity. It becomes a question that cuts to the core of biology itself. Is 0.38 g enough to sustain a human life long-term, or is it just low enough to slowly unbuild us? On the International Space Station, astronauts float in microgravity, 0 g. Their muscles do not need to fight against weight. Their bones do not carry loads. Their hearts do not work as hard to pump blood upward against gravity. Within days, the body begins to adapt. It believes this is the new normal. We know the consequences. In just 6 months on the ISS, astronauts can lose 1 to 2% of their bone mass per month, especially in the hips and spine. Muscles, particularly in the legs and core, shrink despite rigorous exercise. Cardiovascular systems adjust to the easier work, so that when astronauts return to Earth, some cannot stand for more than a few minutes without feeling faint. Their bodies have forgotten what 1 g feels like. These changes are not merely temporary discomforts. Bone density does not fully recover. Tiny structural changes in the skeleton can last decades. The heart slightly remodels itself. Vision shifts as fluids redistribute in the body, pressing on the backs of the eyes. Even the immune system behaves differently, sometimes less effectively, in weightlessness. If this is what happens in zero gravity over months, what happens at 0.38 g over years? This is the Goldilocks question of Mars. Is its gravity just right, or deceptively wrong? Unlike microgravity, Mars still pulls. You will not float. You will still have a down, but your bones and muscles will be doing far less work than they evolved for over millions of years. Every cell of our bodies has been tuned to Earth's 1G. From the strength of our tendons to the structure of our inner ear, our physiology is a record of that constant pull. Recent data from the ISS complicates the story further. Earlier in the space age, some believed that as long as astronauts exercised enough, they could almost completely counter the effects of weightlessness. Treadmills, resistance bands, stationary bicycles, all carefully scheduled, hours per day, like a prescription of motion. But newer, more detailed studies have revealed that even with intense exercise, much of the damage is only reduced, not prevented. Bone loss remains significant. Certain muscle groups, especially deep core stabilizers, weaken in ways we still struggle to fully measure. The cardiovascular system can become less tolerant of changes in posture, like going from lying to standing, something that on Earth we do without thinking. Radiological scans, blood chemistry, genetic markers of stress and aging all tell a more sobering story. On the microscopic level, cells in space behave as if they are under constant, subtle stress. Some markers of aging increase, some repair processes slow. The ISS has become a kind of floating laboratory of human fragility. And yet, all of this data comes from one extreme, near 0G. Mars lies somewhere in between, in a realm we have never truly tested with human bodies. We do not yet know whether 0.38 g will be sufficient to slow bone loss to a manageable level, or whether it will simply stretch that loss out over a longer timescale. We do not know whether lifelong residents of Mars will develop hearts that are permanently too weak, bones too thin, muscles too fragile to endure the stronger pull of Earth. For a colonist born on Mars, returning to Earth may not just be difficult, it may be impossible. Imagine a child taking their first steps under a sky tinged pink by dust. Their bones grow in a world where weight is softly negotiated, not firmly demanded. Their spine lengthens slightly more than it might on Earth. Their posture adapts to lighter loads. Their heart and blood vessels develop without ever needing to push against full Earth gravity. On Mars, that child might be strong, agile, well adapted to their environment. But if they stepped into a spacecraft and journeyed back to Earth, the home of their ancestors would greet them like an invisible crushing force. 1G to them would not be normal. It would be excessive. Their muscles would tire quickly. Their bones, conditioned to carry far less weight, might risk fractures under routine strains. Their cardiovascular system might struggle to keep blood flowing effectively in a world that pulls harder. Rehabilitation on Earth could be long, painful, or in some cases, not fully successful. For some, the transition might be medically unsafe to attempt at all. This is the gravity trap. Not the difficulty of falling into Mars' gravitational well, but the biological difficulty of ever climbing out of it. If Mars colonies become established and generations grow up under its gentler pull, a new question emerges, both scientific and philosophical. Are we watching the birth of a separate branch of humanity? Not in the dramatic science fiction sense of new species with new powers, but in the quiet divergence of physiology over time. Slight differences in bone structure, subtle changes in heart and lung capacity, altered balance systems, different norms for blood pressure and muscle mass. Mars-born humans might need tailored medical protocols. Their normal vital signs might look abnormal by Earth standards. Spacecraft, habitats, even everyday tools could end up designed around the average Martian physique, not the terrestrial one. Over generations, culture will adapt as well. Sports, work, even play, shaped by lighter gravity. A leap across a canyon, a jump to a high platform achieved with ease that would be impossible on Earth. Then there is the deepest unknown of all: reproduction in low gravity. So far, humans have never conceived, carried a pregnancy, or raised a child to adulthood in any gravity other than Earth's. Animal studies in orbit, on rodents, fish, and other species, have shown that early development can be profoundly sensitive to gravity. Bones grow differently. Balance organs in the inner ear may not form typically. Some embryos do not develop normally at all. Gravity is not just a force acting on adult bodies. It may be a silent blueprint for how bodies are built in the first place. What happens when a human embryo floats in 0.38 g? How does the developing nervous system learn up and down? How do cells in a growing skeleton interpret weight, strain, and stress as they lay down bone? How does blood flow in a placenta work when the heart doesn't have to push as hard? These are not details. They are fundamental questions of whether a healthy, thriving generation can be born on another world. Even more unsettling is what we do not know about subtle, long-term effects. Will Martian children experience higher rates of certain conditions, osteoporosis, heart issues, balance disorders, later in life? Or will their bodies adapt in ways we cannot yet predict, forming a new normal that is perfectly suited to Mars, but perhaps forever mismatched to Earth? Recent ISS work with stem cells and organ-on-a-chip technologies suggests that even at the cellular level, mechanical forces like gravity influence gene expression. What genes turn on or off, when, and for how long? On Mars, where every cell would live in 0.38 g from the moment of conception, the entire symphony of gene activity might be subtly retuned. A Mars colony, then, is not just a change of address. It is a long biological experiment that can only truly be run once and cannot easily be reversed. In this light, plans for Mars settlements by 2050 gloss over a profound ethical and medical reality. Colonists who commit to Mars, especially those who raise children there, may be committing to a one-way adaptation. They may not be able to come home in any meaningful physical sense. Their home will be the weaker pull of a smaller world. And yet, this does not make Mars unthinkable. It simply reframes what it means to go. To terraform Mars, to turn it into something more Earth-like, is not only about thickening its atmosphere or warming its frozen ground. It is about confronting the fact that gravity itself cannot be engineered or scaled. We can spin space stations to simulate 1G. We can build rotating habitats on Mars that mimic Earth's pull for a portion of the day. But the ground outside, the dust, the open plains, the canyons and craters, that world will always pull with 0.38 g. The gravity trap is less a danger and more a crossroads. It forces us to see Mars colonization not as a temporary outpost, but as a potential divergence of human destiny. A division not marked by politics or geography, but by the fundamental physics written into our bones. If we choose to step into that lighter pull, we are not just exploring a new world. We are, slowly, quietly, reshaping what it means to be human. We are often told that the future is closer than it looks, that Mars cities are not a question of if, but when, that by 2050, domed habitats will glow softly against the red horizon, greenhouses will sway with hydroponic crops, and children born under a smaller sun will call 2 planets home. But time in space does not move at the speed of headlines. Just as the journey to Jupiter redefines our sense of distance, the journey from concept art to functioning off-world civilization reshapes our sense of time. Decades, not years. Generations, not product cycles. The promise of Mars by 2050 is not simply optimistic. It is a story told on Earth's clock, not the universe's. To see why, we have to slow down. We have to unroll the tape measure of history, technology, and economics, and watch what actually happens when a big idea leaves the realm of imagination and enters the heavy, unforgiving world of engineering. We begin with the technology itself. On paper, the path looks straightforward. First, build a heavy-lift rocket. then a reusable system, then a crewed test flight to Mars orbit, after that, cargo missions, then habitats, life support systems, fuel production on Mars, agriculture, radiation shielding, medical infrastructure, and finally, a colony. On paper, this looks like a linear staircase. In reality, it is more like building a city while every brick is still in the patent office. Each major step, closed-loop life support, reliable radiation protection, large-scale in situ resource utilization, long-duration human health in low gravity, does not exist today as mature, space-tested technology. Many of these steps are still in laboratory phases or early prototypes, the technological equivalent of sketches on napkins compared to the skyscrapers they must someday support. Consider how long it takes for a single technology to travel from first success to everyday reliability. The first jet aircraft flew in the 1940s. Commercial air travel as a common, relatively safe experience did not emerge until decades later. The first computers filled entire rooms in the mid-20th century. The world where billions carry supercomputers in their pockets took more than half a century to arrive. Space hardware moves slower still. Each new system must be designed, built, tested, redesigned, tested again. Every failure is not just a setback, it is a necessary teacher. And space is a harsh instructor. Components that work beautifully in a lab can fail after months in vacuum, under radiation, in extreme temperature swings. A single overlooked detail can mean mission loss. Progress in this environment is measured not just in breakthroughs, but in painstaking iterations. A prototype is a promise. A reliable system is a memory of thousands of things that went wrong first. Now, imagine not just one such system, but dozens, all interlocking. Water recycling, air regeneration, power generation, food production, waste management, hypergravity medicine, autonomous construction, psychological support for crews who will never see an open sky. Each of these systems has its own quiet, unforgiving timeline. The gap between a triumphant demonstration and a scaled, dependable, everyday technology is vast. A rocket reaching orbit once is news. A rocket doing it hundreds of times, safely, cheaply, on schedule, that is civilization. Think of reusable rockets. The concept has existed since the 1960s. Working prototypes began to appear in the 1990s and 2000s. Operational, frequently reflown boosters are only now becoming normal. That journey took about half a century from idea to routine. Now extend that outwards. Closed-loop ecological life support capable of sustaining hundreds of people for years. We are at the early experiment stage. Growing some plants on the ISS is not the same thing as feeding a city through Martian dust storms and equipment failures. If we follow historical patterns, the first working prototypes of such integrated systems might appear in the coming decades. But the road from "we made it work once under controlled conditions" to "it keeps people alive reliably for decades, with spare parts made locally," is long. It does not respect election cycles, investor calls, or media hype. This is where timelines begin to bend. Public narratives often treat each breakthrough like a final step. A rocket test becomes proof that Mars is next. A conceptual habitat becomes a preview of future cities. Time between milestones is smoothed over, compressed into neat graphics and bold date stamps. 2030, 2040, 2050. But time in engineering is not smooth. It comes in bursts of progress, followed by long stretches of integration, testing, waiting, redesign, and sometimes starting over. Behind every sleek animation of a Mars base is a silent question. Who pays for all this, and for how long? When we speak of cities on Mars, we are not talking about a single mission. We are talking about a supply chain that spans planets, operating continuously for decades. We are talking about building and launching fleets of heavy-lift rockets, constructing orbital refueling depots, manufacturing landers, habitats, power plants, and spare parts at industrial scale. Even conservative estimates place the cost of establishing a small, semi-self-sufficient Martian settlement in the trillions of dollars. Not millions, not billions, trillions. This is not unprecedented in human history. We have built trillion-dollar systems before. Global internet infrastructure, national highway networks, entire energy grids, standing militaries. But each of these emerged slowly, across generations, fueled by large economies, tax bases, and geopolitical imperatives. Mars has no voters, no natural market, no immediate economic return that justifies its cost in a traditional sense. There is no gold rush under the red dust, no obvious commodity so valuable that it funds entire interplanetary logistics chains. For now, Mars is funded by something more fragile: inspiration, prestige, strategic positioning, and the ambitions of a few wealthy institutions and individuals. These are powerful motivations, but they fluctuate. Economies cycle, governments change priorities, corporations pivot. A trillion-dollar commitment over half a century requires a level of sustained political and financial stability that our species rarely maintains without interruption. This is where the promises of corporations and agencies often tilt away from reality. In public, the timeline must always be near enough to be exciting, but far enough to be safe. Year 2050 is perfect. Close enough to say, within your lifetime. Far enough that most current decision-makers will be retired when the date arrives. Corporations, especially, live in a delicate balance between vision and valuation. Bold timelines energize investors, attract talent, and justify massive spending in the present. A promise that a Mars city is only 20 to 30 years away functions as both inspiration and shield. It buys patience, yet the engineers working on the hardware tend to speak a different language when the microphones are off. Ask mission planners, not in press conferences, but in closed workshops, private correspondences, hallway conversations, and a quieter consensus emerges. Many of them will say, a sustained human presence on Mars is possible, but it will almost certainly take longer, cost more, and be more technically convoluted than public roadmaps suggest. Some describe the first true outpost, with rotating crews and partial in-situ resource utilization, arriving in the late 21st century. Some push sustainable multi-hundred-person settlements into the 20-teens, not because they lack imagination, but because they live in the harsh arithmetic of mass, energy, failure rates, and human physiology. We have been here before. In the 1950s and 60s, visionary scientists and writers confidently predicted nuclear-powered passenger rockets, spinning space stations with artificial gravity, and lunar bases by the year 2000. Some artists drew bustling Mars cities for the same time frame we now inhabit. They extrapolated from the dizzying pace of the early space age and assumed the curve would continue. It did not. Instead, we got a handful of brief lunar visits, an orbiting laboratory with a crew of fewer than a dozen, and a long pause before private companies revived the dream of reusable launch. The predictions were not foolish. They were simply blind to the friction of politics, economics, and the messy, non-linear nature of technology development. They imagined a world where space budgets kept growing, where every program succeeded, where accidents did not reshape public will. The same thing happens in the opposite direction too. In the early 20th century, few imagined commercial airlines linking continents for ordinary people within a few decades. In computing, some early pioneers underestimated how deeply their work would saturate civilization. Our history of prediction is not a record of failure. It is a reminder that we are bad at seeing how constraints will evolve over time. So when we hear cities on Mars by 2050, we should not dismiss it as impossible, but we should translate it. In the language of technology and history, that promise often means, if everything goes extremely well, if funding never collapses, if there are no catastrophic accidents, if each major unknown resolves in our favor, then by around mid-century, we may be entering the early, fragile, experimental phase of what could, generations later, become a true off-world civilization. The danger is not that we dream too big, It is that we compress those dreams into timelines that reality cannot sustain. When dates slip, as they almost always do, people feel misled. Enthusiasm turns to cynicism. Support erodes. The very projects that need decades of patient investment are left vulnerable to the short attention span of our culture. To think clearly about Mars, we must learn to think in planetary time. The storms on Jupiter do not care about our deadlines. Radiation on Mars does not soften because a launch calendar says crew departure. Biology will not adapt faster simply because a press release promises a colony. The universe moves at its own pace. Our task is not to force it to match our expectations, but to align our expectations with the realities we uncover. If we do that, if we accept that 2050 is not the era of Martian cities, but perhaps the dawn of serious hard-won presence, then something liberating happens. Mars ceases to be a marketing milestone and becomes what it truly is, a multi-generational project. A cathedral we begin knowing that we will not live to see the final spire. In that light, the question is no longer, will there be colonies on Mars by 2050? But, what foundations can we honestly lay now so that someone, someday, might walk under an alien sky and call it home? The answer to that question may be far less glamorous than glossy renderings. It may involve humble robotic missions, slow building infrastructure, uncelebrated experiments in life support and human health. Yet it is precisely in that quieter work that the real future of Mars will be forged. The timeline, then, is not a deception of malice, but of compression. We compress centuries of civilizational effort into a few decades of marketing. If we uncompress it, if we stretch it back out to match the scale of the challenge, Mars does not become less reachable. It becomes more real. If the dream of turning Mars into a second Earth dissolves under closer inspection, the story is not over. It simply changes genre. Terraforming becomes less a quick makeover and more an epic saga, one that might not end on the Martian surface at all. When we strip away the glossy paintings of red deserts and blue skies, what emerges is not the end of human expansion, but a different map. One where survival does not depend on forcing Mars to become like us, but on learning how we might bend, adapt, and cooperate with worlds that are indifferent to our expectations. In this version of the future, Mars is not a blank canvas. It is a harsh collaborator. We begin below the surface. Burying a city sounds like defeat. In reality, it may be the only honest truce we can make with Mars in the near term. The underground city model accepts everything Mars refuses to change. The radiation, the thin atmosphere, the wild temperature swings. Instead of trying to fix the planet, we duck beneath its armor. A few meters of rock and regolith can provide the shielding that an entire lost atmosphere cannot. Imagine walking through a pressurized tunnel carved into ancient basalt, the ceiling strengthened with metal ribs grown from in-situ resources. Above you, frozen dust storms claw at the empty air. Below you, pipes hum softly, circulating heat, water, oxygen, an artificial ecosystem woven into Martian stone. Light does not come from the sky. It is imported, fiber optic cables capturing what weak sunlight there is at the surface and funneling it downward, supplemented by high-efficiency LEDs tuned to the colors plants love most. Hydroponic farms stretch along cavern walls, columns of green spiraling toward low, glowing ceilings. In this world, outside is a toxic vacuum. Inside is a garden. Underground cities could grow like roots. First, small pressurized habitats tucked into lava tubes, natural tunnels formed when ancient flows of molten rock hollowed themselves out and cooled. Then, larger chambers, melted or mined into the subsurface, connected by transit tunnels and airlocks. The surface becomes a place of work, not of life. Robotic construction crews assemble solar fields and nuclear reactors. Humans make brief, suited journeys to maintain the machines, then retreat back into the sheltering rock. Mars, for now, remains a planet we visit from the inside out, but there is another path that barely touches the soil at all. Above Mars, space is empty, but not useless. Instead of fighting a low-gravity, high-radiation surface, we could step sideways and build where physics is more forgiving, in orbit. Rotating space habitats, great wheels, cylinders, or toruses slowly tumbling end over end, offer something Mars never will: adjustable gravity. Spin a ring fast enough, and the floor becomes down. Not perfectly, not exactly like Earth, but close enough to keep bones and muscles from surrendering to weightlessness. Picture a ring habitat in Mars orbit. On the inner surface, a band of landscape curves overhead. Modular homes, laboratory blocks, green strips of algae ponds and trees. The sky is not blue, but a panoramic window of stars, with Mars hanging like a rusted coin below. One section of the ring could simulate Martian gravity for training and research. Another, closer to Earth's gravity, could become a long-term home for those who need their bodies to last decades, not missions. Radiation shielding comes from mass, and mass is easier to gather in orbit than it sounds. Regolith launched from Phobos and Deimos, Mars's small moons, could be bagged and layered over habitat hulls like a protective shell. Water tanks, food stores, even waste, everything heavy becomes part of the armor. In these rotating worlds, Mars becomes an object of study and resource, not a place to casually stroll. Landers and ascent vehicles carry crews up and down like elevators between two profoundly different environments: the fragile bubble of human life in orbit and the harsh laboratory of the surface below. It is possible that the first true Martian cities will never touch Martian soil. Meanwhile, on the ground and in orbit, a quieter, slower experiment could be unfolding, one that stretches far beyond human lifetimes. If terraforming Mars is impossible on human timescales, it might still be conceivable on planetary ones. Robotic terraforming imagines a world where machines arrive centuries before we do. They do not breathe. They do not age. They do not care that the sky is thin and the soil is laced with perchlorates. They just work. Swarms of autonomous excavators could mine ice, haul it to processing plants, and crack it into hydrogen and oxygen. Greenhouse gases, carefully chosen for maximum warming effect and minimal side reactions, could be manufactured and steadily released into the atmosphere. Reflective dust or orbital mirrors might dim or brighten specific regions, nudging climate patterns on a scale that feels almost glacial. Other machines could slowly detoxify soils, bury perchlorates deep underground, or trap them in stable compounds. Microbial seeds, engineered to survive cold, dryness, and radiation, might be tested in sealed bioreactors, learning how to metabolize Martian chemistry without ever being allowed to escape. All of this unfolds over centuries, perhaps millennia. Planets change slowly, and Mars has already been cold and thin-aired for billions of years. Our interventions would be whispers compared to the storms and impacts that shaped it. But whispers, over enough time, can become stories. The paradox is simple. By the time Mars is even marginally more habitable, we may be very different from the humans who launched the first machines. That leads to a more unsettling, and perhaps more realistic, vision. Instead of changing Mars, we change ourselves. Biological engineering is already reshaping medicine and agriculture on Earth. Move that frontier outwards, and the question shifts from how can Mars support humans to what kind of humans could thrive on Mars? Imagine future colonists whose blood carries enhanced radiation-resistant compounds, inspired by extremophile bacteria and tardigrades. Lungs and cardiovascular systems tuned to operate efficiently in lower oxygen environments. Bone density pathways altered so that Mars's weak gravity does not silently eat away at their skeletons. Skin that heals more quickly in low-pressure conditions. Microbiomes adapted to closed-loop habitats. Even circadian rhythms rewired to match the 24.6-hour Martian day. This is not fantasy so much as extrapolation. We are already editing genomes, growing organoids, and planning therapies that modify human biology at its roots. Extending these techniques to prepare people for alien worlds is less a question of science and more of ethics. At what point does a Martian-adapted human stop being simply human? Who gets to decide which traits are acceptable enhancements and which are irreversible divides? Would a lineage engineered for Mars ever feel truly at home back on Earth? Or would two branches of our species slowly drift apart, like planetary orbits that no longer cross? Hybrid solutions may be where reality gently settles. No single strategy will bridge the gap between us and Mars. Underground cities could anchor the first outposts. Rotating habitats could protect long-term residents and serve as hubs of trade and research. Robotic terraforming might slowly tip the planet towards slightly friendlier conditions. Biological engineering could make the difference between constant medical crisis and stable, if altered, life. Together, these approaches form a network of compromises rather than a single heroic leap. Mars ceases to be a stage for simple conquest and becomes a complex ecosystem of technologies, ethics, and timelines. And yet, there is an uncomfortable question lurking at the edge of this vision. What if Mars is not the best place to attempt any of this? Look inward, to a world we have written off as hell. Venus, beneath its crushing atmosphere and sulfuric clouds, hides a secret most people forget. It is almost exactly Earth's size and mass. Its gravity is close to our own. In that single metric, the pull on your bones, Venus is more like home than Mars ever will be. The surface is lethal, true, but 50 to 60 kilometers above it, in the thick atmosphere, there is a layer where pressure and temperature begin to match Earth's. There, floating habitats, vast airships filled with breathable gas, which is itself buoyant in Venusian air, could, in theory, drift like high-altitude cities. Radiation is lower at that altitude than on Earth's surface. Sunlight is abundant. The world we call a furnace might, in its skies, offer gentler conditions than Mars's ground. Farther out, beyond Mars and the asteroid belt, another candidate waits in the cold. Europa. Locked in orbit around Jupiter, Europa is encased in ice. But beneath that ice, evidence suggests a global ocean, warmed by tidal forces, may churn in perpetual darkness. On Europa, we would not walk under open skies at all. We would live in ice caverns and pressurized domes, drilling downward into black water that has never known sunlight. If life exists anywhere beyond Earth, many scientists quietly place their bets here, in the hidden sea of a distant moon. From a survival standpoint, an ice roof shielding us from radiation and a vast subsurface ocean providing water and raw materials is not a bad starting point. Compared to building a breathable atmosphere from scratch on Mars, melting your ceiling and filtering the results begins to feel strangely practical. Venusian cloud cities, European ocean bases, Martian lava tube towns, orbital rings turning slowly above a rusted world. None of these fit the simple poster of a lone astronaut staring across a red desert toward a distant blue sun. They are messier, stranger, and more demanding of patience. But they share something the polished dream of fast terraforming does not. They acknowledge what the universe has actually given us. Mars is not a failed Earth waiting to be fixed. Venus is not just a warning. Europa is not merely a cold rock in Jupiter's shadow. Each is a different kind of challenge and a different kind of invitation. Our future among them will not be written in one grand gesture, but in a series of careful, uncertain experiments. In stone, in orbit, in code, and in DNA. We drift now, not between planets, but between promises. The glow of animated concept art, glossy press releases, and grand timelines for million-person Mars cities fades behind us like the receding light of a distant star. Ahead lies something less visually spectacular, but far more important. The quiet space where ethics, expectations, and reality collide. The journey to Mars is not just a technical question, it is a moral one. Because behind every artist's rendering of domes on red horizons, there are real people who may one day step into that thin Martian air and bet their lives on the accuracy of what we say today. In the same way, Jupiter bends the path of a spacecraft, Hype bends the trajectory of public imagination. A slight exaggeration now, a glossed-over risk there, and suddenly we are on a new course, one that may not lead where we think it does. This is why the truth matters. Over-promising is its own kind of gravity. In the early days of any great venture, enthusiasm is fuel. It pulls in funding, talent, and attention. But when expectations race ahead of what physics, biology, and engineering can support, a different force appears: disillusionment. History has seen this pattern before. Nuclear power was once promised as too cheap to meter. The space shuttle was pitched as a routine space truck, with rapid reusability and low cost. In both cases, reality was more complex, more fragile, more expensive. When space agencies, companies, or charismatic visionaries speak of Mars colonies in the 2030s or 2040s, of tens of thousands of residents living in relative comfort, they are not just inspiring. They are making an implicit contract with the public. Trust us. This is possible. This is near. This is worth your investment. If those timelines slip by decades, or the difficulties prove far harsher than advertised, trust erodes. The public begins to see not an epic generational project, but another overhyped dream. That erosion is not abstract. It shapes budgets, election promises, and long-term funding cycles. A single high-profile failure, framed as the Mars generation's broken promise, could lock space exploration into a winter of skepticism for years or even decades. Children who once looked up with wonder might learn instead to roll their eyes. In spaceflight, a missed gravity assist can cost you years. In public trust, a missed promise can cost you generations. Beneath the graphs and mission plans lies a more intimate question. What do we owe the people we send? A Mars colonist is not a tourist. They are not booking a return flight. They are stepping into an environment we know is hostile, to face risks we do not fully understand, for a duration we cannot easily limit. We know some of the dangers: radiation that quietly shreds DNA over months and years, dust laced with perchlorates that could inflame lungs and poison soil, low gravity that may irreversibly damage bones, muscles, vision, and perhaps even the brain. But there is another category of risk, the ones we suspect but cannot yet measure. How does a human psyche adapt to a sky that is always the same? To the knowledge that Earth, blue and alive, is months away even in an emergency? To living inside a sealed habitat where every breath, every sip of water, every scrap of food is mediated by machinery that cannot fail for decades? When we talk of pioneers and frontier spirit, it is easy to wrap these unknowns in romantic language. Yet romance does not substitute for informed consent. Ethically, any colonization effort has to grapple with a difficult balance. We cannot wait for all risks to be known. Exploration always involves uncertainty. But we also cannot pretend that uncertainty is minor or easily solved with slogans. If volunteers step onto a Mars-bound spacecraft believing they are entering something akin to a rough version of Antarctic research life, when the reality is closer to a permanent high-risk medical experiment, then we have crossed a line, not in engineering, but in honesty. To choose Mars with eyes open is courage. To be nudged there with half-truths is something else. Beyond individual lives lies a wider question that circles our planet like an invisible ring. Where should we point our resources? Mars missions are not cheap. Mega rocket development, life support research, radiation shielding, closed-loop agriculture, autonomous construction, each of these requires billions of dollars and the brightest minds on Earth. Meanwhile, under our own sky, other emergencies gather: rising seas, collapsing ecosystems, resource scarcity, health crises, and the quiet, grinding inequalities that shape who thrives and who survives. For some, the answer is simple: we must fix Earth first. For others, the logic flows differently. Becoming multiplanetary is our insurance policy. We protect Earth by ensuring humanity isn't bound to one fragile world. Both perspectives hold a piece of the truth. The ethical tension arises when Mars is sold not just as a scientific endeavor or a long-term safeguard, but as a near-term escape hatch, as if the passengers of a burning ship could leap casually to another vessel waiting just beyond the flames. Mars will not be a refuge from climate change or political instability anytime soon. If anything, early Mars habitats will amplify our vulnerabilities, not solve them. Every kilogram of water, every gram of oxygen, every spare part will be hard-earned. If we honestly framed Mars as a centuries-long project of learning, experimenting, and slowly, carefully building outposts, the resource debate would shift. It would no longer be about abandoning Earth, but about extending Earth's reach, in parallel with healing it. The real ethical question is not Mars or Earth. It is, can we tell the truth about how hard Mars will be and still choose to pursue it without neglecting the crises at our doorstep? Paradoxically, honesty does not dim the dream of Mars. It refines it. When we acknowledge that a self-sustaining Mars settlement by 2050 is unlikely, we create space for a different kind of progress, one built on incremental testable steps rather than sweeping declarations. Clear-eyed dialogue about the challenges can redirect funding toward technologies that matter for both worlds. Closed-loop life systems, advanced recycling, resilient agriculture, new energy storage. Promote precursor missions that confront the hardest problems head-on. Years-long stays in simulated Mars gravity. Full-scale tests of radiation shielding. Long-duration habitat trials in extreme Earth environments. Invite more disciplines to the table. Psychologists, ethicists, sociologists, doctors and anthropologists, joining engineers and physicists to design not just ships and suits, but lives that can be lived with dignity. Transparency does something else too. It transforms spectators into participants. When the public understands not just we're going to Mars, but here is precisely what stands in our way, they can invest emotionally in the process, not only the finish line. A mission that admits its limits becomes a shared puzzle. Every setback, every partial success becomes part of a narrative of learning rather than a story of broken guarantees. Inspiration has a radiant power. It can pull a child toward science, a student toward engineering, a society toward long-term thinking. The image of a human footprint in red dust is potent because it symbolizes more than a place. It symbolizes a choice to reach beyond what is necessary into what is possible. But inspiration fueled by distortion carries a hidden cost. If we claim that terraforming Mars is a project of a few centuries instead of, more realistically, perhaps many millennia, if it is possible at all, we set up a fragile hope. When that timeline inevitably shatters, some will turn away not only from Mars, but from science itself, convinced that it overpromises and underdelivers. There is another way to inspire, by showing the true scale of the challenge and our willingness to face it anyway. Imagine framing Mars not as an imminent second Earth, but as a laboratory for mastering extreme sustainability, where every atom is tracked. A mirror held up to our own planet, forcing us to see how rare breathable air, liquid water, and complex life really are. A long, slow apprenticeship in living beyond home, measured not in press conferences, but in decades of patient work. The wonder does not vanish when we admit how hard this is. It deepens. It shifts from, we will conquer Mars, to, we will learn if we can belong there at all. That kind of wonder is more durable than hype. It can survive delays, failures, and revisions, because it is not anchored to a specific date or headline. It is anchored to curiosity. In the end, the ethics of Mars colonization hype come down to a simple, human question that echoes across the interplanetary void. Do we value truth enough to carry it with us, even when it slows us down? Every mission we launch, every plan we announce, is a message to the future. It tells later generations what we believed, what we were willing to risk, and how honestly we face the unknown. If we choose to cloak Mars in oversimplification and marketing, we may reach it sooner on paper, but with weaker foundations in reality. If instead we choose clarity about radiation, gravity, timelines, resources, and the unresolved mysteries of long-term human survival off-world. We may move more slowly, but we will move with integrity. Mars does not care what stories we tell about it. Its thin air, its cold deserts, its silent canyons will not bend to our optimism. But we can choose the story we tell about ourselves. A species that flees from its problems and dresses escape as destiny, or a species that confronts its limitations, heals its home, and then reaches outward with humility, accepting that the journey to other worlds begins with an honest reckoning on this one. In the soft hum of imagined spacecraft, in the quiet hours when our planet sleeps, the truth is not our enemy. It is our compass. And if one day human footsteps do press into Martian soil, it may be that what got us there was not the volume of our promises, but the precision of our honesty. As our journey across red deserts and silent canyons comes to an end, Mars begins to look less like a glossy poster of the future, and more like what it truly is: a beautiful, hostile archive of planetary history. The simple story we're often told, rockets, domes, and cities under a salmon sky, is only the cover of a much denser book. Behind that cover are the details we've traced through this voyage. An atmosphere so thin, it cannot hold warmth or shield us from cosmic radiation. Soil laced with perchlorates that turn every garden into a chemistry experiment. Water that exists more as a rumor in the rocks and ice than as flowing rivers. Radiation that seeps invisibly into every habitat wall. Gravity that is too weak for bones and hearts shaped by Earth. And timelines, promises of bustling colonies by mid-century, that stretch and warp when they collide with physics, biology, and engineering reality. None of this means Mars is off limits. It means Mars is honest. Terraforming a world is not an act of will, but an act of time. The energy needed to thicken an atmosphere, warm a planet, and reshape its surface is closer to what stars and geologic ages accomplish than what a few human decades can provide. The real future of Mars is likely not a quick transformation into a second Earth, but a patient weaving of fragile human habitats into an uncompromising alien landscape. Mars colonization is possible, but not in the way marketing departments suggest. It will start small. Underground or half-buried habitats, not glass domes under open sky. Life support systems that behave less like technology and more like artificial ecosystems, cycling every molecule of air and water. Astronauts who are less like explorers planting flags and more like caretakers tending an experimental biosphere on a world that never asked for one. To reach that future, we need something more powerful than optimism. We need honesty. Honesty about the timescales involved, not years, but generations. Honesty about the methods, robotic precursors, cautious human outposts, relentless testing of life support systems, and medical studies we have barely begun. And honesty about the risks, not as deterrents, but as coordinates on the map we're trying to draw. The hidden challenges of Mars aren't reasons to turn back. They are the curriculum of a species that wants to grow up among the planets. Every new measurement of radiation, every drill core searching for ice, every biological experiment in partial gravity is a sentence added to our textbook of interplanetary life. The more we learn, the less Mars is a fantasy, and the more it becomes a real place, with real limits, real dangers, and real possibilities. Our responsibility is to keep asking difficult questions, even when the answers are inconvenient to dreams of quick conquest. What does it mean to alter a whole world? How do we protect any native chemistry, or even potential biology, that may linger underground? How do we build a future on Mars that isn't only technologically impressive, but ethically considered? If you'd like to keep exploring questions like these, you can help this journey continue. Tap like so this story doesn't vanish in the algorithmic dust. Subscribe if you'd like more nights of drifting through quiet worlds and complicated truths. And in the comments, share where you're listening from, what corner of Earth you're imagining Mars from tonight. If you want to support this channel a little more deeply, you can also join the YouTube membership. It's completely optional, but it helps us keep making long, careful voyages like this one, at a time when slow, thoughtful science is easy to overlook. Mars will wait for us. It has waited for billions of years. The question is not whether we can reach it, but how honestly we choose to tell the story of getting there.